Hi guys, today I will discuss to you about the multiple motors, feeder conductors, and short circuit and ground fault protection calculations. This is still part of the design, installation, and maintenance series that I am going to present. We are still on that design stage. I would like to ask you to please subscribe and click the like button and the notification bell and click all so that you will get all my videos that I will be uploading. So this is our scenario. We want to calculate the feeder conductors and the short circuit and ground fault protection or the breakers for multiple connected motors. These are the feeder conductors that we are going to determine, and the feeder short circuit and ground fault protection device or our overcurrent protection device. For the single motor branch circuit conductors, I have already discussed in my previous videos, so I suggest that you go back and first watch my lecture on single motor branch circuit conductors, and also for the single motor short circuit and ground fault protection device, because this is somehow a prerequisite for understanding this multi-motor feeder and short circuit and ground fault protection calculations. Now let us go to the code rule for conductor ampacity. The National Electrical Code says that for the conductor ampacity of the several motors or motors and other loads, they shall have ampacity not less than the sum of each of the following. So number one, 125% of the full load current rating of the highest rated motor. Number two, sum of the full load current ratings of the other motors in the group. Number three, 100% of the non-continuous non-motor load. Number four, 125% of the continuous non-motor load. Now let us review some code definitions just for a clear understanding. So for a branch circuit, it is the conductors between the final overcurrent device protecting the circuit and the outlets or the loads. So this is our branch circuit. For the feeder, it is considered as all circuit conductors between the service equipment or either a source of a separately derived system or other power supply source and the final branch circuit overcurrent device. So this is our feeder. And what does this mean for a continuous load? It is a load where the maximum current is expected to continue for 3 hours. So if it is less than 3 hours, we can consider it as non-continuous load. So this is the given. We have a three-phase system. So we want to determine the circuit breaker or the main circuit breaker, short circuit and ground fault protection, and the feeder conductors. So from the NEC tables, for single phase motor FLC, and for the three-phase motor FLC, in the 230 volt column, for 1 horsepower we have 8 ampere, For 5 horsepower, we have 28 ampere. And for the 3-phase table, under 230 volts, for the 2 horsepower, we have 6.8 ampere. For the 5 horsepower, we have 15.2 ampere. For the 7.5 horsepower, we have 22 ampere. Now we are going to determine the feeder conductors. So we have given here, as we got from the table, 7.5 horsepower, we have 22 ampere, 3-phase. 5 horsepower, 15.2 ampere, 3-phase. 2 horsepower, 6.8 ampere, 3-phase. 5 horsepower, 28 ampere, single phase. And 1 horsepower, 8 ampere, single phase. So now, what is the highest rated motor? So as per the code, the highest rated motor is not the 7.5 horsepower. It's not depends on the horsepower, but it depends on the current, the FLC that the motor have. So if you are going to do the balancing of the motor loads for phase 1, phase 2, and phase 3, for L1, L2, L3, for motor 1, we have 22 ampere in all phases. Motor 2, 15.2 ampere in all phases. Motor 3, 6.8 ampere in all phases. Motor 4, we have 28 ampere. We will put it in L1 and L2 only because this is a single phase. And motor 5, we will put it in L2 and L3, 8 amperes. So the total current for each phase is L1 72 ampere, L2 80 ampere, L3 52 ampere. So we have to use the phase with the highest total current, which is L2. And if you notice, we have 5 motors, so all 5 motor currents is found in this phase. Now we will go to the calculations. So as per the code, 125% of the full load current rating of the highest rated motor, we have 28 ampere times 1.25. And number 2, sum of the full load current ratings of all other motors in the group. So these are the other motor currents: 22 ampere, 15.2, 6.8 plus 8. And also number 3, 100% of non-continuous non-motor load. So here in this our calculation, it is not included, so there is none. If there are non-motor load which are non-continuous or operating less than 3 hours, so you can include this as well. And number 4, 125% of continuous non-motor load. So if you have a continuous load, a non-motor load like lighting, which is operating more than 3 hours, so you can include it as well. But here in this our example, it is not considered. Now let us calculate the total current for feeder conductor sizing. So now we have 28 ampere times 1.25 plus 22 plus 15.2 plus 6.8 plus 8 plus 0 plus 0. So it is total 87 amperes. Now looking at the table for the conductor ampacity, since loads are motors, though it is below 100 ampere, we have to use 75-degree column. for the motors. From the table, we get 100 ampere ampacity for 30 square mm, or this is equivalent to number 3 American wire gauge conductor, or it is number 2 American wire gauge in PEC or Philippine Electrical Code. So therefore we have to use 3 by 30 square mm THW or THSN stranded copper conductor with 100 ampere capacity. So we can see it here in this table for conductor ampacities, allowable ampacities. This is the 75-degree column. So tracing the 100 ampere, we got number 3 American wire gauge. Now for the code rule for the feeder, short circuit and ground fault protection or the circuit breaker. Motor feeder, short circuit and ground fault protection, part 5 in NAC 2017. So this provision only states that to calculate for the short circuit and ground fault protection, we have to add the following. Number 1, the largest rating or setting of the branch circuit, short circuit and ground fault protection for any motor, or also for any hermetic refrigerant motor. This is also applicable, plus the sum of full load currents of other motors of the group. And also just in case where all motors have the same rating or setting, we have to consider at least one of them as having the largest rating. So we can use it in the same calculation. Now with this given rating of the motors, our aim is to determine the feeder, short circuit and ground fault protection device. Now what is the largest rating or setting of OCPD in this case? In this case, it is the 5 horsepower single phase motor because it has a 28 ampere, which is the largest current in this circuit. This is the 28 ampere, so we have to use the 5 horsepower single phase. Now for the calculation, rating or setting of highest rated motor, short circuit and ground protection device, we have 28 times 2.5 for the inverse time circuit breaker. We have now 70 ampere trip. So this is our breaker, 70 ampere trip. This is the highest. Plus sum of the full current of all other motors. We have 22 ampere, 15.2, 6.8 plus 8. So total current for short circuit and ground fault protection sizing, we have 70, the largest protection device, plus the other currents of other motors, 70 plus 22 plus 15.2 plus 6.8 plus 8. Now we got 122 amperes. From the table, standard ampere rating for fuses and inverse circuit breakers, 122 ampere is not exactly available. So we have to use 125 ampere trip. We can see it here in this table. This is 125. There is no exact 122. The lesser one is 110, and next to 125 is 150. So we can use 125 in here. Now to summarize, now we have to use 3 by 30 square mm THW THSN standard copper conductor with 100 ampere ampacity. This is the feeder conductor that we have to use. And for the short circuit and ground for protection, we have to use 125 ampere trip, 150 ampere frame. This ampere frame you can see also in the tables of the manufacturers, or OEM, original equipment manufacturer, and in the catalogs of the electrical products. And we have to mention also the number of poles, 3 poles, since we have a 3-phase. And don't forget, we have always to indicate the CAIC, or the kiloampere interrupting capacity. Here I assume 15 CAIC, but it is still to be determined. As discussed in my previous videos, the CAIC rating must be determined using the short circuit calculation. So in here, this is only an assumption. And also you have to indicate what type of breaker are you going to use. So here it is the inverse time circuit breaker, and it is an MCCB, a molded case circuit breaker. So I would like to invite you again to subscribe, click like, and click the notification bell and select all, so that you will get all the videos that I am going to upload. I hope that it will help you, and thank you. May God guide you in your